Okay, so now for problem 33, we want to identify the vertex and axis of symmetry for the graph of the function f of x equals 3x squared minus 24x plus 43. Now, first I'm going to go ahead and find the axis of symmetry. And that's going to look like x is equal to negative b over 2a for the form ax squared plus bx plus c. Now here, b is our negative 24, a is 3, so this is going to happen at x equals negative 24 over 2 times 3, which will give us 24 over 6, which is just 4. So the axis of symmetry is at x equals 4. Now the vertex happens along this axis of symmetry that we have. So our vertex will be what is f of x at the axis of symmetry, so that'll be what is f of 4. That is equal to 3 times 4 squared minus 24 times 4 plus 43, which will give us 48 minus 96 plus 43. Plugging that in gives negative 5. So vertex at our x value is 4 and our y value is negative 5. Next, we have that an apple is thrown vertically into the air. Its height in feet above the ground at time t is given by this function. So what we want to do is solve for t when h of t is equal to 0. So to set that up, I'm going to give h t is equal to 0, or negative 16t squared plus 48t. Now if we notice, that function, it still says 0 on the left-hand side. That's equal to, we factor out a t, we're left with negative 16t plus 48. So now we have two different pieces that could each be 0 to satisfy that. So the first one is just t equals 0. Now t equals 0, that just happens at right before it's thrown, right as it's thrown. The next piece we have is that negative 16t plus 48 is equal to 0, which gives that 48 is equal to 16t, or t is equal to 3. If we think about it, if we throw something up in the air, it'll be at an elevation of 0 when we throw it, and then it'll be at an elevation of 0 when it lands. So that t equals 3 is going to occur as the ball lands. Next, we want to know what the maximum height that the apple reaches is and what time it reaches that. So to determine that, we want to look between our two zeros. So our vertex is going to occur between the two zeros. So just kind of like at the average, 3 plus 0 over 2, that gives us at 1.5. Now h of 1.5 is equal to negative 16 times 1.5 squared plus 48t. Evaluating, that gives us h of 1.5 is equal to 36 feet. So maximum at max of 36 feet at 1.5 seconds. And we want to make sure to include our units. Moving on, we are supposed to assume a quadratic function has the following properties, here and here. And we want to know the domain and range for this function. So before we even start, we know that a quadratic function has range over all real numbers. There's not any point where that breaks. So So the domain here is just going to be from negative infinity to positive infinity. That one was nice and easy. Now moving on, we have information about the vertex and information about our zeros. So what I'm going to do is kind of graph this out a little bit. So we have at -2, we have a 0. We have at +8 is another 0. Now our vertex is going to be at 3 and a height of 12.5. So that's going to be here. Now if we think about it, our function, this is our vertex, our zeros are down at -2 and +8. Our function is going to look like this, right? So that means that we have a maximum here at that 12.5. Nothing in that function is going to go above it. But it goes all the way down to -infinity. That means that our range is going to be from -infinity up to +12.5. That 12.5 is going to be included because we do have a point where it is equivalent to that. So it is included on the interval. Next, we are to assume that a quadratic function of this form intersects the x-axis exactly one time. We want to determine what does that mean about our values of a, h, and k. So if we think about that, what that means, touches the x-axis exactly one time, the only value of a parabola that I guess is there at exactly one time is the vertex. There's no other point in the parabola where it has the same y value. Any point aside from that will have a second point. So like if we look at, I'll draw an example. If we have a parabola that looks like this, here at the vertex, we only have one point that has that value. If we were to look above, we have 2 points that have the same value. So what that means for this question is that if we draw our axis, along that axis, could be here, could be there, could be anywhere, our vertex is going to be at x = 0. Or is going to be at y, a y of 0, which means that k must be 0. Now, as far as h and a go, a is really the biggest one that has to be restricted, because if we think about it, if a, let's just say if a is equal to 0, then we're just going to have a line that looks like the x-axis. So in addition to k has to be 0, we also know that a cannot. And again, that's just because if a were 0, we'd have the x-axis and it would touch it not just once, but an infinite number of times. So that's something we have to avoid. And then h just translates it to the left or the right. That doesn't really impact how many times it touches the x-axis, so we're okay. That doesn't need to be restricted at all. So just h is any real number. Okay, on to question 37. First, we have this big function. We want to find the leading polynomial and the degree of the function. So I guess if we think about it, we're going to have, if we expanded this out, we'd have a -5 in front. We'd have a 4x minus 3, 4x minus 3, and so on, times 3x plus 1, 3x plus 1. Now, if we think about what is actually included in our function, the only parts that will impact the leading coefficient and the degree are the x terms inside of here, and then the -5 in front. So here, what we really need to worry about is that -5 term, 4x being multiplied 5 times, and 3x being multiplied twice. And if we were to evaluate that, we would end up with an x to the 7th term. So that means the degree is 7. And our leading coefficient, if we were to evaluate negative 5 times 4 to the 5th times 3 squared, we would end up with a leading coefficient of negative 46,080. Now we want to determine the zeros and their multiplicity. So looking back at our function real quick, erase this. We know that we have these two terms. Those terms are the ones that could potentially give us zeros. So if we were to look at it, say, okay, well, what if 4x minus 3 is equal to 0? And what if 3x plus 1 are equal to 0? Now here on this first one, this would give us 4x is equal to 3, or an x value of 3/4. The other one, we'd have 3x equals negative 1, or x equals negative 1/3. So now if we were to talk about multiplicity, though, we have x at 3/4. That comes from 4x minus 3, and those occur 5 times. So we have x at 3/4, multiplicity of 5. And then we'd have x equals negative 1/3, multiplicity here. This comes from this, so we'll have multiplicity of 2. Moving on, we want to fill in the blanks. So as x goes to negative infinity, what is f of x going to go to? So what really impacts us the most here is going to be our leading coefficient and the degree that we found earlier. Those are going to be the most impactful portions of this. So our leading coefficient, again, is negative 46,000. We have times x to the 7th. So if we think about it as x goes to negative infinity, this part is going to go to positive infinity. Oh, sorry, that part is going to go to negative infinity. So we'll have a negative number here times a negative number here. So f of x is going to trend to positive infinity. Then as x goes to positive infinity, similarly, we're going to look at negative 46,080, x to the 7th. As x goes to infinity, this part is going to go to infinity. We'll have a negative number times a positive number that will give us approaching negative infinity. Okay, so now for number 38, we want to find a formula for a polynomial with the following characteristics. We want our answer in factored form. So first we know that it's going to be a cubic function, 3rd degree, which means that we will have a, we're going to have 3 different factors. We also know that it's going to have zeros at -5 and 2 with no other unique zeros. So what we can do is just go ahead and say, okay, well, we know we're going to have an x plus 5. We know we're going to have an x minus 2. And then we know there's no other unique zeros. So one of these is going to have to be raised to a second power. For this sake, I'm going to use x plus 5 and just check from there. We know it wants to pass through the point 1, 3. So that means that f of 1 should be equal to 3. Which if we plug in f of 1, that's going to look like 1 plus 5 to the second power times 1 minus 2. Which is the same as 6 squared times -1, which gives us a -36. Now, we want that to have a value of +3. So what I'm going to do is I'm going to add a factor in front and say, okay, well, let me multiply this in front. That's not going to change our zeros. That doesn't change our degree either. So we have -36a then is going to be equal to +3, which gives us that a is -1/12. This means that we have -1/12 x plus 5 squared, x minus 2. Now what we want to do is check the end behavior because that's the last portion that we need to look at. So as x goes to negative infinity, we'll look at this and see what it does. So we'll have negative 1 over 12. This portion here is going to become, it's going to approach negative infinity squared. And then the other portion again will be negative infinity. So here, this is going to become a positive middle term. So we're going to have negative 1 over 12 times infinity times negative infinity. Positives or negatives will cancel out. So we get as x goes to negative infinity, y is approaching positive. Then as x goes to positive infinity, we want to check the behavior of that as well. So we'll have negative 1 over 12. X plus 5, as x gets larger and larger, is going to approach infinity. X minus 2 will do the same. So here we only have one negative. So as x goes to positive infinity, y is going to go to negative infinity, which is indeed what we wanted. So that means that this function is a correct solution. It satisfies all of these characteristics. Now moving on, we want to take this polynomial and reduce it to two quadratic factors. So what I'm going to do is try and factor this by grouping. So we have 2x to the fourth minus 11x squared plus 5. I'm going to go ahead and just kind of change this to 2x to the fourth minus x squared plus negative 10x squared plus 5, just to see what I can do. Now if we factor both of these a little bit, that's the same as x squared times 2x squared minus 1 times, plus you bring out a negative 5 from the second term. And then when you look at that, we also end up with 2x squared minus 1. So now what we want to do is factor these out of the whole thing, which will give us x squared minus 5, 2x squared minus 1. Next, we want to find all real zeros of P. So what that's going to look like is when x squared minus 5 is equal to 0, and 2x squared minus 1 is equal to 0. So this first part, this is going to give us x squared is equal to 5, or the value of x is plus or minus the square root of 5. Then for the second one, we will have 2x squared is equal to 1, which gives us that x squared is equal to 1/2, or x is equal to plus or minus 1 over root 2. So those are all 4 zeros of our function. Next, we want to make a rough sketch and graph of P, so including real zeros and end behavior. So what we want to do is I'm going to go ahead and draw a thing. If we think about our function, we want to go ahead and check the end behavior of that. So if we think about as x goes to infinity, that means that f of x, as x goes to infinity, that means we'll be looking at our 2x to the fourth and on and on and on. As x goes to infinity, this is going to approach infinity. So as x goes to positive infinity, y will do the same. As x goes to negative infinity, and 2x to the fourth and this will approach infinity as well, since it's being raised to the fourth power, so the negative will go away. So y will also approach infinity. And now, going back to our graph, plotting our zeros. we're going to have 1 at root 5, 1 over root 2, and then at our negative values. So it's going to come down from positive infinity to here. It's going to have a vertex down here, vertex up here, vertex down there, and it's going to go back up to positive infinity. And that is about what our graph is going to look like. Now, for number 40, we want to make a sketch of a polynomial that has these properties. Go ahead and sketch what that would be like. We're going to have 1 positive 0. So I'm going to draw a point here. And then 2 negative ones. One of them will have a multiplicity of 2. We have a positive y-intercept. So I'm just going to draw a point right here. And we know that as our end behavior, as x goes to negative infinity, y goes to negative infinity. So we should have something down here. And as x goes to positive infinity, y also goes to negative infinity. So it's going to look like that as well. So now, I guess all that's left to do is sketch our function. The right-hand side will be nice and easy. I'm just going to draw like that. The left-hand side, this is where it gets a little bit trickier. It's not too bad, though. We just have to pay attention to this part right here. So I'm going to choose that first 0 as having a multiplicity of 2. That means it's going to hit and then bounce right back up. And then it goes through the second 0 down to negative infinity. And that will satisfy all 3 of these conditions. Perfect. Moving on to number 41, we want to suppose p of x is a polynomial with degree 4, with real coefficients, zeros at -5, 0, and 3, passes through this point where a is a positive real number, and the long-run behavior of p is this. And we want to figure out which zeros could potentially have a multiplicity of 2. So what I'm going to do first is I'm just going to draw out our graph. We have a 0 here, here, and here. We know it's 4th degree, so one of these is going to have a multiplicity of 2. And it goes through a positive point over here. So it's going to be positive. Now, what I'm going to do is just kind of go through what each of these could look like. So as x goes to, I'm also going to plot what we have here. So as x goes to negative infinity, p of x goes to negative infinity. So we're going to have something that looks like this. And as x goes to positive infinity, p of x will also go to negative infinity. So now, if we were to assume this one here has a multiplicity of 2 at 0, we know that it would hit, come back down. Then we can't cross the x-axis again until we go through the origin, but we have to hit this point. So we know, by process of elimination, that our 0 at -5 cannot have multiplicity of 0. Now, okay, moving on to the other ones. We go up through -5, we hit here, then it hit 0, bounce back up again, come down again. We notice that does satisfy all of our conditions. So 0 could have a multiplicity of 2. That's pretty helpful. That's nice and easy, helps us to see what's going on our graph. Now that last one, we want to look at if 5 has a multiplicity of 2. So we're going to go up here, cross that point, come down through 0, hit 5, and bounce back down. Which, look at that, that also satisfies all of our conditions. So we're going to have that 0 and 3 are possibly have orders of 2. Moving on to question 42, we want to find each of the following for the given rational functions f and g. So first, I guess we're just going to look here. So I guess my first step would be to try and see if we can factor this out at all. That'll help us figure out what our asymptotes might be, or if there's any like holes and like that kind of thing. So how I'm gonna do that is I'm just gonna keep the top the same, can't really factor that out. But if we notice in our denominator, we can factor this out. That'll become x minus 2 and x plus 8. Here, this is the same as that, so that is going to be the same as 1 over x minus 2. That'll help us find our horizontal asymptotes, or sorry, our vertical asymptotes, because this, whenever this bottom portion is 0, so if x minus 2 is 0, sorry, x minus 2 is 0, that will be our vertical asymptote. So that means our vertical asymptote is at x equals positive 2. Now our horizontal asymptote, that will be what happens at x goes to infinity. So if we're looking at 1 over x minus 2, as x goes to infinity here, we're going to get closer and closer to 1 over infinity, which is going to become 0. So our horizontal asymptote is going to be at y is equal to 0. Now, if there's any holes in the graph, we want to go ahead and figure that out in part B. So holes in the graph are going to occur whenever we have a binomial in our denominator and also our numerator, one that could be canceled out. So here, if we remember, that x plus 8 is what was canceled out here. So that is going to be x plus 8 is our whole discontinuity, which means that this is going to be set that equal to 0. We end up with at x equals negative 8, there's a hole. That means that when x equals negative 8, y is going to be 1 over negative 8 minus 2, which will give us negative 1 over 10. So there's a hole at negative 8, negative 1, 10. And then finally, our domain is what we want to look at here. So if we think about the domain, we already know that it breaks at x equals positive 2 from the vertical asymptote and at x equals negative 8 from our hole. So that domain is going to be from negative infinity to negative 8, unincluded because 8 is a whole, from negative 8 up to 2. 2 is also unincluded because it's an asymptote. Then from 2 up to positive infinity. Moving on, we want to find an example of a rational function with a vertical asymptote at x equals negative 5, 0 at x equals 3, a hole here, and also these properties. So what I'm going to go ahead and do is just say, okay, we know we have a vertical asymptote at x equals negative 5, which means that in our denominator, we should have an x plus 5. We also know we have a 0 at x equals 3, which means that in our numerator, we're going to have an x minus 3. And we have a hole here. So similar to earlier where we knew that, okay, we have a hole because this is, because the x plus 8 is being canceled out. That will mean that similarly, we should have an x plus 6 in the top and the bottom. And then finally, as x goes to infinity, y should go to negative 2. As x goes to negative infinity, y should also go to negative 2. So if we think about our rational function, the limit as x goes to infinity or negative infinity is going to be determined by our leading coefficient. So I'm just going to put an a term in front to act as a multiplier. We have a times our leading coefficient in the top is going to be x squared. Our leading coefficient in the denominator is also going to be x squared. So as x goes to, this is just going to become a as x approaches infinity, which means that we should have, if you remember, we wanted to have a limit of -2, that means that a is going to be equal to -2. So our example function is going to be -2, x minus 3, x plus 6 over x plus 5, x plus 6. And this is going to satisfy all the requirements that we were given. Next, for problem 44, we want to evaluate these two limits. So first, we're going to look at the limit as x goes to positive infinity. As x gets bigger and bigger, these two terms are to be the only terms that will impact it. The -x plus 1 in the top is going to become more and more negligible, and the same with the 5 in the denominator. So as x gets really, really, really big, these terms are going to matter less and less. So that's going to be about the same as evaluating 3x squared over 2x squared. Notice the x squareds cancel out. We're just left with 3 over 2. And that is going to be our limit. This next part, as x goes to negative infinity, 8x to the -3 plus 5x to the -1 plus 1. As x gets really, 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 really large, of course it's getting negative, but it's still getting pretty large, this is going to start to approach 0. Because 8x to the -3, that's the same as 8 over x cubed. So as x gets bigger, this thing is going to get smaller. It's going to keep getting really, really small. Eventually, it's going to be so small that it's negligible. Same thing here, whereas 5x to the -1, same as 5 over x. As x gets really big, this is going to get really small. Now all we're left with is 1. Moving on to number 45, we want a possible formula for a rational function described here. So g is going to have two vertical asymptotes, x equals -2 and x equals 3. That means that we want to have x plus 2 and x minus 3 in the denominator, just because those are going to serve as our asymptotes. Now, we also want a horizontal asymptote of y equals 0. I'm going to come back to that. Here, though, this is going to mean that we have exactly 1, 0. And that's going to be at x equals 5. Or sorry, x equals 5, which means that we'll have x minus 5 in our numerator. Now, I'm also going to go ahead and move on to this part where we know that it passes through the point 4, 0.5. So when x is 4, 4 minus 5, sorry, I'm going to add a little multiplier here just so that we can solve for that. We have an a times 4 minus 5 over 4 plus 2, 4 minus 3. That is going to give us -a over 6 times 1, and that is going to be, again, equal to 0.5, which means that a is equal to -3. So we now have instead of a -3. If we think about our horizontal asymptote now, of y equals 0, that means that as x gets large, we want this to approach 0. So if we think about it as x gets large, we're going to have -3. We're going to have an infinity on top, and we'll have two infinities in our denominator. They'll kind of cancel out. We're left with 1 in our denominator. So this condition is also met, which means that g of x could be -3 x minus 5 over x plus 2 x minus 3. Perfect. Moving on, we want to determine which rational function has a hole in the graph at x equals 3. And we want to give a reason for that choice. So first, that means that we're going to want an x minus 3 in the numerator And secondly, we also want x minus 3 in our denominator. So looking at this first part, we can factor this into x plus 3, x minus 3, just because it's a difference of squares, but this part will not. So therefore, we know that we can eliminate a. Moving on to the second part, we can factor this into x minus 3, x plus 1, which will give us that x minus 3 in the top, x minus 3 in the bottom, which means that b could be right, or that b is a correct answer. Here, we're going to have the one that cancels out is x plus 3, so we would have a whole at x equals negative 3, but that's not what we're looking for. We want at x equals positive 3. So this one is also not quite right. And then finally, this one's going to factor to x times x plus 3. Nothing here is going to cancel out, so we know d is also not correct. So here, b is right, b, because it has an x minus 3 in the numerator and denominator. Moving on to our last question, number 47, we want to check which description best matches the graph of a rational function. So before we even look at the descriptions, I'm going to say we're going to have 0 at x is equal to a negative, horizontal asymptote at y is equal to a positive number, and then a vertical asymptote at x is equal to a negative number. So these are the three items that we want to pay attention to when we're looking at our descriptions. So first, A, we have a 0 at x equals 4, vertical asymptote at x equals negative 3, and a horizontal asymptote at y equals negative 4. So right off the bat, we know that our 0 should be negative, so A is not correct. Moving on to B, we have 0 at negative 3, asymptote at negative 6, horizontal asymptote at 7, which could be right, but the thing is that our 0 should be more negative than our vertical asymptote, because if we look, our 0 is to the left of the vertical asymptote. Here, this is describing a function with a 0 over here and not where it actually is. So B is also not going to be correct. And finally, for C, we have a 0 at x equals negative 4, vertical asymptote at negative 2, that is correct, it should be less negative, and a horizontal asymptote at y equals 3, that looks correct.